Welcome to today's paper reading. Today's paper is titled Branch-Train-MiX, Mixing Expert LLMs into a Mixture of Experts LLM. This paper was published on the AR14 preprint by Sainbayar, Sukhbaatar, and colleagues from FAIR at Meta. The primary objective of this research is to develop efficient methods for training large language models, LLMs, to possess specialized capabilities in multiple domains such as coding, math reasoning, and world knowledge. The proposed method, named Branch-Train-MiX, BTX, initiates from a seed model that is branched to train domain experts in an embarrassingly parallel fashion, achieving high throughput with reduced communication costs. After individual experts are trained asynchronously, BTX integrates their feedforward parameters into mixture of expert, MoE, layers and averages the remaining parameters, followed by an MoE-finetuning stage to learn token-level routing. This approach generalizes two special cases: the branch-train-merge method, which lacks the MoE-finetuning stage for routing, and sparse upcycling, which omits the asynchronous training of experts. Comparative analysis shows that BTX achieves the best accuracy-efficiency trade-off among alternative approaches. Large language models, LLMs, have demonstrated remarkable capabilities across various tasks, including code generation and solving mathematical problems. However, training these models is resource-intensive, requiring significant computational power and data. The process often involves synchronization across multiple GPUs, which can be a bottleneck and is susceptible to hardware failures. To address these challenges, several methods have been proposed, such as the branch-train-merge (BTM) approach, which trains models independently on different data subsets, and the mixture of experts (MoE) approach, which activates only a subset of parameters. In this paper, the authors introduce a new method called Branch-Train-MiX (BTX), which combines the benefits of BTM and MoE, aiming to improve training efficiency and model performance. Figure 1 illustrates the Branch-Train-MiX (BTX) method, which involves three main steps. First, the method branches from a pre-trained seed large language model, LLM, by creating multiple copies of it. Second, these copies are trained separately on different subsets of data to produce expert LLMs. Finally, the expert LLMs are mixed by combining them into a single LLM using mixture of experts feed-forward layers, followed by fine-tuning the unified model. This approach allows for embarrassingly parallel expert training, reducing communication costs and increasing training throughput, while still forming a unified model that can be further fine-tuned. The related work section highlights several key areas of research. In asynchronous training, Xian et al. 2015 introduced elastic averaging to reduce synchronization, while Dillard et al. 2023 demonstrated the effectiveness of Nesterov momentum for less frequent synchronization. Li et al. 2022a proposed the branch-train-merge method for independent parallel training. In the context of mixture of experts, MoE, Rozière et al. 2017 used top-K routing. Roller et al. 2021 showed that fixed routing can be effective, and Xian et al. 2024 found that MoE can match dense LLM performance with fewer parameters. Continual learning is also relevant, with Awasthi and Sarawaji, 2019, focusing on domain experts, Rozière et al. 2023, showing fast convergence for domain-specific training, and Xiao et al. 2024, finding that starting from a code expert is beneficial for training a math expert. The branch-train-mix methodology consists of three main stages: branch and train, mix, and variations. In the branch and train stage, the authors initialized n expert LLMs from a seed model and trained them in parallel on specific datasets. This approach allows for linear scaling of training throughput and reduces communication costs. The mix stage employs a mixture of experts approach, combining domain expert models by fine-grained mixing within each transformer layer. This involves top-K routing and averaging self-attention weights. The variation section explores additional techniques such as load balancing to prevent dead experts, different routing methods, and methods for splitting and blending experts to enhance domain generalization. In this section, we discuss the experimental setup based on Llama 2 pre-training. The Llama 2 7B model is used as the seed model for our experiments. We trained domain experts by continuing training on specific datasets, math, code, and Wikipedia. These experts were then mixed into a mixture of experts MoE model. We compared our approach to several baselines, including the original Llama 2 models, dense and sparse upcycling, and branch-train-merge. Evaluation was conducted using zero and few-shot performance on benchmarks that test math reasoning, code generation, world knowledge, and general reasoning skills. The results show that our domain experts excel in their respective tasks, and the MoE model improves performance across specialized domains without regressing on other tasks. Table 1 presents the performance of individual domain expert LLMs on representative tasks, comparing them to the seed model Llama 2 7B. The data reveals that the code and math experts significantly outperform in their respective domain tasks. Specifically, the math expert achieves high scores in GSM-8K in math tasks, while the code expert excels in human eval and MBPP tasks. Interestingly, the Wikipedia expert demonstrates superior performance in the natural questions task. This suggests that the math expert's training, which includes many math subjects, aids in achieving the best score on MLU. These findings underscore the specialized capabilities of each domain expert LLM. Table 2 presents the aggregated performance of BTX, Branch-Train-Merge, compared against various baselines, including generalist and specialized pre-trained models, across multiple capabilities and benchmarks. The table highlights that BTX significantly improves performance in expert domains such as math, coding, and world knowledge, without compromising on other tasks like common sense reasoning. Notably, BTX approaches the performance of specialized models like Llama 7B and Code Llama 7B in their respective domains, while outperforming them in non-specialized areas. Additionally, BTX demonstrates better compute efficiency compared to alternative data matching methods like dense and sparse upcycling, and outperforms BTM, Branch-Train-Merge, by a large margin, indicating the benefits of MoE, mixture of experts, fine-tuning. Overall, BTX proves to be a more compute-efficient method for continued pre-training, robust to task interference from multitask learning, and even surpasses Llama 2 13B on most tasks despite using less training compute. Table 3 presents a detailed comparison between BTX and sparse upcycling with compute matching, CM, highlighting the differences in performance and training efficiency. The table shows that BTX, which includes an expert training stage, outperforms sparse upcycling, CM, in terms of both individual domain performance and average performance. Additionally, BTX demonstrates higher throughput and a more balanced performance across various domains, indicating its superior compute performance trade-off. Figure 2 illustrates the performance of BTX models compared to various baselines in terms of training budget. On the left, the graph shows that BTX models, indicated by different circle sizes representing varying active parameters, achieve higher average performance across all tasks compared to models like Llama 2 7B and 13B. The right side of the figure normalizes performance across different domains, highlighting significant improvements in coding and math tasks for BTX, even surpassing Llama 2 13B. This demonstrates BTX's superior compute efficiency and robustness in multitask learning scenarios. Table 4 presents the results of ablations on various routing methods used during BTX training. The average score is calculated based on performance across key tasks such as GSM-8K, Human Eval, Natural Questions, Arc Challenge, and MLU. The table highlights different routing strategies including no load balancing, freezing experts, and blending experts. Notably, the top two routing method demonstrates a favorable balance between performance and efficiency. Table 5 presents the results of ablating different training strategies for BTX. All variants were initialized from the same experts and trained for a total of 10 billion tokens during mixture of experts, MoE-finetuning. The study found that MoE training without load balancing performed worse on the coding task, Human Eval, but had higher math, GSM-8K, accuracy. Freezing the feedforward modules initialized from each expert, and only training the rest of the MoE model had little impact on performance across all tasks, suggesting that individual experts already gained sufficient domain knowledge during the branch-train stage. Figure 3 illustrates the BTX routing decisions of tokens at various layers to different experts across multiple domains. The domains include code, math, world knowledge, and reasoning tasks. The figure highlights that top 2 routing with load balancing ensures a more uniform distribution of the load between experts compared to top 2 without load balancing. This balancing effect shifts the token probability distributions towards lower scores, especially in the final layers of the model, contributing to fairer routing. Notably, load balancing revives the code expert, which becomes dominant in the math and code domains. Table 6 illustrates the token routing decisions made using the top 2 routing method with load balancing across 3 key domains: math, GSM-8K, code, human eval, and knowledge, natural questions. The table highlights how tokens are directed to specific experts, such as Wikipedia and Llama 27b, math and Llama 27b, and code and Llama 27b. Additionally, it underlines tokens that are routed to in-domain experts, providing a clear view of the distribution and specialization within these domains. In this study, the authors introduced Branch-Train-MiX, BTX, a method designed to enhance the capabilities of large language models, LLMs. BTX involves training multiple specialized copies of a seed LLM across various domains, which are then merged into a single mixture of experts, MoE, model through fine-tuning. This approach not only increases training throughput and scalability during the initial parallel training stage, but also improves the performance of the final LLM in the MoE-finetuning stage. The experiments conducted suggest that the performance of a generalist LLM can be significantly boosted by continued training on datasets rich in specialized knowledge and skills using the BTX method. Furthermore, the BTX approach has been found to be more computationally efficient compared to training a larger generalist LLM or several separately specialized LLMs. These findings provide valuable insights into how computational resources should be allocated during late pre-training to achieve a robust generalist model. Moving forward, the authors plan to address the limitations of the current method and explore further optimizations to enhance the generalist model even more. In this paper, the experimental results on BTX are promising, but the potential has not been fully explored due to compute limitations. Specifically, only 3 domains and 4 experts were experimented with, and a simple MoE implementation was used. Future work should involve training on more domains, potentially using unsupervised domain discovery, and increasing the number of experts to enhance the efficiency of the MoE model. Additionally, optimizing the MoE implementation with more complex techniques could reduce training time. The question of whether experts in MoE should specialize in specific domains is also an area for further investigation. Although experts were explicitly tied to certain domains in this approach, specialization did not naturally emerge during training. Some experts showed partial domain specialization after MoE fine-tuning. Finally, future work could explore a broader range of compute allocation ratios between expert training and MoE training, as well as different data mixtures for MoE fine-tuning. In this section, the authors acknowledge several individuals for their contributions. Margaret Lee, Kushal Tirumala, and Luc Setlamore provided valuable discussion and feedback. Ardidoro Pagnoni, Sachin Garurangan, and Mike Lewis also contributed additional feedback. Furthermore, Andrew Cohen and Arun Babu assisted with the training implementation, and Emily Dinnan was acknowledged for her role in the project. Thank you for watching.